Hey there, and welcome to a review of solubility equilibrium. If this is your first time watching it, a suggestion is to go slow. There are a lot of problems in this, and it's mainly focused on the mathematics. We're going to look at the process of ions dissolving from a solute and how they establish an equilibrium with the solvent to create the solution that is being analyzed. So it's important to realize that solubility is a physical process, and it's the process of a solute dissolving into its ions, a positive and a negative ion. It is not a reaction, and the role of water is to overcome the intermolecular forces of the solute to allow it to separate into individual ions. So our goal here is to describe what solubility equilibria is, determine the solubility product, which is a term we'll learn, calculate ion concentrations and molar solubility. We'll stop there, and we'll call that the end of part A, because then we'll move on to double displacement reactions and precipitates and how they, in part B, also represent an equilibrium. So before we begin, it's important to understand why we study these concepts, and we'll use a biochemical connection here. What you see is a kidney, and within the kidney, its role is to filter the blood. It separates waste nutrients from the blood and allows them to pass into the urine. One of the things it does is to filter calcium as well as phosphate. However, when these ions mix, a reaction forms. And this is one of many. So we have calcium ions, and we'll use net ionic equations here, plus the phosphate ion. Right, and because this is a reaction in solution, we will form calcium phosphate, which is insoluble. It's supposed to be a 2, and then a solid there, and then it's balanced from that point on. Don't forget the atoms and the charges need to balance out. So while this is in solution, we talked about it before, in almost all cases, solutions are reversible. Right? When the ions dissolve, they can be recrystallized, and they can form the solute again, or the solute can dissolve into the ions. So in this case, if we have this reaction going on in our kidneys, what happens as the concentration of calcium increases? Well, because it's a reactant, there will be a shift right towards the products, and more calcium phosphate will form, which is the solid. So for people high in calcium and phosphate within their blood, their ion concentrations, they have to be careful about the amount of calcium that they intake, because it can drive the reaction towards forming a precipitate, which can result in larger stones. Now, a larger portion of a kidney stone is what's known as calcium oxalate. So we won't study that, but it's the exact same process. It's a more complex ion than phosphate ion, and it involves carbon and oxygen and hydrogen together. But it represents the same product. So high calcium diets can lead to the formation of kidney stones, and there's research examining this effect quantitatively. So now that we establish something that's happening in our body and gives us a little bit more purpose to study this, let's go over some terms. Solubility is the amount of solute that can dissolve in a solvent. Right? Generally, the universal solvent is water. And you noticed in grade 11 when we studied solutions that almost everything was dissolved in water in those cases. It's not the only one, but it's the major one. So different ways of measuring solubility are units per volume of solvent. So the first unit represents the amount of the solute, and the second one represents the amount of the solvent. So there's several different ways, as you can see here. Grams of solute per milliliter, so how much of a solid we can dissolve in water. Milligrams, same idea, only smaller unit. Or moles per liter, if we're working with concentration. So now we can convert between these using the molar mass. And we'll try a quick problem with that first. So the first problem is, and we've just got the Word document here to give us a bit more space. the mass solubility of lithium carbonate, so Li2CO3, is equal to 1.3 grams per liter. And that means for every 1 liter of water, 1.3 grams will dissolve. That's very low. Just for the record, we'll put that there. Determine the molar solubility. So we were given mass solubility. Molar solubility would be in moles per liter. So the first thing we're going to do is need to convert that grams that we were given into moles. So we'll need the molar mass for that. So the molar mass of lithium carbonate, if we take the periodic tables that we have here and add up all of the individual values, right, which you should try. And as always, I suggest you pause the video, try it, and then come back for the solution. So you should have found that it's 73.89 grams per mole. Right, and if we set this up as a ratio, right, do our dimensional analysis, grams, we can cancel out the grams from there, and we'll be left with 1.76 times 10 to the negative 2 moles per liter. So that means that value in moles can dissolve in 1 liter of water. Now what we did here was the mass solubility divided by the molar mass, as you can see in the question as the hint there. Right? We just don't have formal variables or an equation for that. So division is like the inverse. Because the units are grams per mole, right, to divide by that fraction would be like inversing it, so it's 1 mole over 73.9 grams, and then multiply the inverse. So we'll go back to here, and again, we've got to get used to working with different units and formats. So let's look at a solute dissolving in water. Okay, and solutes are mainly ionic compounds that we work with in this scenario. When an ionic compound enters water, even if it's insoluble, a very small amount of that solute will turn into its ions, A plus and B minus. Remember that the positive ion is always written first and the negative ion second. So the solute itself is a solid, and then once it's added to water, the ions are aqueous because they're dissolved. Notice how we don't have water here though. And the reason for that is it's not a reaction. Okay, this is, like I said off the bat, it's a physical process. So the water is just helping this happen. The charge is balanced and the atoms are balanced, so we won't show water here. Now, if we look at this, if something is highly soluble, that means it's formed a lot of ions. So it's going to be, it will have a large K value because most of the products are forming, which are the ions in this case. That means it will dissolve. An insoluble compound has a low K value, which means it favors the reactant, and a precipitate forms because the solid does not dissolve. So precipitate's a solid that is not dissolved once placed in water. Because we're working with two different states, we have the solid and their aqueous ions, this is a heterogeneous equilibrium, which means not all terms are in the K expression. Okay, so we have to remember that. And you can see by looking at it, the solid will be excluded, and only the ions make up that. So when we relate this to the equilibrium calculations that we've done, we get this process called the solubility product, and it's noted as KSP. Before we worked with KEQ, now we're going to work with KSP. So the salt, which is compound AB, dissolves into its ions. And if K is products divided by reactants, as a quick review, it is A times B divided by AB. But because the solute is a solid, it's canceled out, and this is technically over 1, which we don't need to show. So for all solutes, this is called the solubility product. And one of the reasons for that is it's the product of the ion concentrations that dissolved. So we talked about this. It's not included because it's a solid, right? What we can use this law for is to predict or analyze how much of that compound will dissolve before a precipitate forms. So if we need to know how much of something will dissolve in a sample, this is the process that we'll use. And we can use this in terms of pollution statistics, compounds within the bloodstream, and there's a lot of applications to medicine within this. One of the most important things to keep in mind, okay, as we're talking, equilibrium for a solute represents a saturated solution. So it's the point where the maximum amount of solute can dissolve. Any more solute than this, and a precipitate forms. And we'll use PPT as a short form for precipitate. We'll just put that there so we can see it. Okay, so it's very important to understand that it's at the saturation point where all of the solute has dissolved into its ions, and anything past that will be oversaturated. So let's look at an example here. Knowing with what we just said. Determine the solubility product of a solution of calcium phosphate if the concentrations of its ions are given. So to determine KSP, we need an equation, because an equation will tell us what the products and the reactants are, which make up the law. Calcium phosphate is the reactant here, because it will be placed in the water. Now, using our solubility table, you'll see that calcium phosphate is a solid. And all solutes will start off as a solid as the reactant. Then once it enters water, it will dissolve into its ions. So calcium and phosphate, and then we'll add their charges. Okay, and because they've dissolved, they're aqueous. Now remember, even an insoluble product from the solubility series will dissolve a little bit. It just means that less than 1 gram per 100 milliliters will dissolve. All right, we learned that threshold in grade 11 again, and it's just a continuation of those processes. So if we write the KSP equation here, right, it's products over reactants, so we have calcium, right, and we have to balance this. Okay, that's important here because it will be raised to its exponent. It's an elementary process. Dissolving is one step. And don't confuse the charges for the exponents. It's the coefficients. Okay, that become those. So now given that, and the fact that the ions are listed in order, okay, we can just punch those in. And take care, because you're working with scientific notation and exponents, we want to make sure that we get the right values here. So we have these all lined up, and if you've tried that, you should get 8.48 times 10 to the negative 33. And remember, K is unitless. So what does this mean? This is a very small value to the negative 33. That's not a mistake. So this is very insoluble. So that means that these ion concentrations here are the maximum concentration of the ions that can be there before a precipitate forms. Any higher than that, and we'll see little solutes sitting on the bottom of a beaker. But at those concentrations and below, there will be no precipitate forming. Right? So if we want to know about maximum solubility, this is something we would consider. So now we'll look at what the ion concentration means and how it's actually related to the amount of solute, because we don't usually measure the ion concentration. We relate that back to what the solute itself is. So as a review, the ion concentration is given by the compound, right, and the subscript. So the subscript tells you the ratio of ion to molecule. So the concentration of the ion will be the concentration of the compound multiplied by its subscript. So let's write that out. Ion concentration is equal to the subscript in the formula times the concentration of the molecule or substance. All right, now that just saves us a stoichiometric step. The other thing to remember is that because we're working at equilibrium, it means we have a saturated solution. So if we ever look at K versus Q, we can determine if something will be unsaturated or oversaturated. what we're assuming is that all the precipitate is dissolved into its ions at the saturation point. So all of the solute is converted into its ions. So we'll use these two concepts to go through an example now. Now, given this value here, right, we're working with the compound magnesium fluoride. So we're being asked to determine the KSP value. So again, to do that, we need an equation. And it needs to represent the solute dissolving into its ions. So magnesium fluoride is MgF2. And because it's dissolving, it's a solute, it's solid at that point. And once it breaks up into its ions, we write an equilibrium reaction. We have magnesium with a charge of 2, and it's aqueous. And again, we're assuming that some of it's dissolved, plus 2 F minus AQ. So, given that, we can see that this is balanced now. Okay, and if we write the KSP expression, products over reactants, so for solubility, we only ever have the ions multiplied by each other. Okay, squared, because we have the coefficient of 2 there. Now, in the question, we were told molar solubility of. So that doesn't tell us anything about the ion concentrations. What it tells us is that the concentration of magnesium fluoride is equal to 2.76 times 10 to the negative 4 moles per liter. So what this means, and it's important to understand this, this is the maximum moles of MgF2 that dissolves in 1 liter. So that would be the saturation point. So if we're trying to find the saturation point, which is KSP, that describes the point at which there's maximum solubility, we're assuming that it's at this case. Okay, so that value, molar solubility, is its maximum concentration. All right, when it's a saturated solution. So if that's the case, and a saturated solution is at that concentration, that means all of the magnesium fluoride dissolves. All of it dissolves at this concentration. So what we can say is that the concentration of the ion, like we said, is equal to the subscript times the concentration of magnesium fluoride. So let's just make an aside here. For the concentration of Mg2+, its subscript in the equation is 1 times the concentration of magnesium fluoride. So its concentration will be the same as the concentration of magnesium fluoride, because when it splits up, that one molecule produces one ion. So when all of it splits up into its ions, it's all as that ion. Now for F minus, because there's a subscript of 2, when all of the MgF2 dissolves, there's going to be twice as many fluorine molecules, which means it'll have twice the concentration. So we'll multiply that value by 2. So we can use the property of the solute, its solubility, to determine what the maximum ion concentration will be. And now we can sub that in. So we can say KSP is equal to Mg2+ minus squared. So we'll plug our values in. We can't forget to square that. Right, and when we work that all out, we're going to get a fairly sillily low number again. And that's unitless. Right. So again, let's interpret this. What does it mean? So if the maximum solubility of magnesium fluoride is 2.76 times 10 to the negative 4 moles per liter, that means it has a KSP of 8.4 times 10 to the negative 11. So that'll let us determine how much of any sample will turn into ions. Now, a quick aside, magnesium fluoride is a coating used on glasses as an anti-scratch protector. So it's good that it has a low solubility, or else if it had a high solubility, it would dissolve off of the glasses in the rain or with sweat or anytime they got wet. So materials are chosen based on their solubility. Sometimes we want high values and sometimes we want low values. So we'll finish off with another example here. Okay, calculate the molar solubility of zinc hydroxide where the KSP is given. So in this case, we want to know, based on a standard value, how much zinc hydroxide will dissolve. So we'll start off with an equation. Just erase that there. Okay, so when it dissolves, we'll get zinc 2 plus as aqueous and OH minus ions. And there will be 2. We don't want you to go anywhere yet. All right, so there's our reaction. And again, we're being asked to find the concentration of zinc hydroxide. Its maximum concentration. So to do that, remember what we had said earlier. Again, the ion concentration at equilibrium, right, when it's a saturated solution, is equal to the subscript times the concentration of the molecule. So if we can determine the ion concentration at equilibrium, then we can use that to relate it back to the molecule concentration. And to find out any concentration at equilibrium, we had learned before to use an ice table. So we'll start off by using an ice table, and then we'll substitute it back into this. So we have our reaction written out already. We're just going to scribble that out because solids don't go into an equilibrium, and we'll go here. All right, our ions, our products, which means there is nothing to start with. They have no concentration. We will gain them relative to their coefficients, so plus x and 2x. We've got x and 2x at equilibrium. And again, we learned this. If we can't solve an ice table for equilibrium values, use the K expression. So KSP in this case is products over reactants, which is just OH minus squared, right? And the reactant is the solid, so it only has a value of 1. We know the KSP value from the question. We know that that is x, we know that that is 2x, and that is squared. So when we simplify that out, right, don't forget the exponent applies to everything in that case. Right, so we have 7.7 times 10 to the negative 17 equals 4x cubed when we factor in the x beside that as well. Okay, and then we'll isolate for what x represents. Go up here. X equals 2.68 times 10 to the negative 6. So let's think about what this means now. So we can plug that value back in to find out the ion concentrations, which means the concentration of zinc is equal to x, which is equal to 2.68 times 10 to the negative 6 moles per liter. Now that's important, because now that we know the concentration of one of the ions, we don't need to know both, but it'll work. We can relate it back to the concentration of the molecule. So we can say zinc and the molecule are in a 1-to-1 ratio, which means their concentrations will be equal. So we can say, therefore, the concentration of zinc hydroxide, right, 1-to-1, is equal to 2.68 times 10 to the negative 6 moles per liter. So that's combining almost everything we've done in the unit up until this point. Right? And what this tells us, the understanding we want here, this is the maximum concentration per liter, so the maximum number of moles per liter that will dissolve. So if I have a 5-liter solution, I can work backwards to figure out the number of moles of solute that will actually dissolve in that. All right. So we're going to end part A there. Right, you can go back and rewatch that as needed. And in part B, we'll look at precipitation reactions, double displacement, and how we can predict how much of that product can be recovered.